This is not going to be a big deal when you're squaring things. Like no one cares. X squared, no one cares. We know what x squared would be. 5 squared would be, 2 squared would be. This is actually going to be handy when we have to do square root functions or e to something. Because those, we don't know the exact value for those. Okay. So we are going to start with the example of e to the x. So I think e to the x is given to you on your graph. Yeah. So let's move on here. So here is e to the x. Just like in calculus, like so far we did our sum of the series, the more terms you have, the better your approximation gets. The same thing here. The more terms you have, the better your approximation gets. Okay? So if I have to just approximate what is the value at this point, you can make a slope, right? You know how to make a slope. So that would be a linear function. The linear function will be just one term and you can approximate it. If you want to get better with approximation, maybe linear is not helpful. We should get as close as possible to this over here. So maybe I should probably draw a quadratic, maybe? That would help. Or maybe it should be a cubic, or maybe even better. So this. So these are all the ways that we're going to write our expansion in to figure out the approximation, okay? So for that, f of x is e to the x, okay? And we are saying we're going to center this around c equals 0, so which means we're going to be looking at this point. This is c equals 0. And we know what e to the 0 is. What is e to the 0? 1. Okay, we already know that. Obviously, it's not going to be helpful for e to the 0. But what if I have to do e to the 1? Then it's going to be handy. Oh. Okay, so if we want to make the graphs have a similar shape at the point x equals c, this is x equals c. So if you want to have a similar shape, which means I can draw a slope for that. So that would be f prime of x. In this case, f prime of c will be p prime of c. Okay? Slope at that point would be f prime of 0, which would be the same as p prime of 0. Okay? We are actually deriving the series here. That's what we are doing. If a polynomial is given to you or a function is given to you, what would this look like when I expand it? That's what we are trying to do. E to the x is a function, yes, but we're going to expand it. Like that's what goes in your calculator actually. The expansion behind it. Because calculator, you're not going to enter every single thing for your calculator. E squared, e to the 3, e to the 4, e to the 1.5. That's not going to happen. So on the calculators, it's probably a rule that's going to work no matter what those numbers are. What is a rule? How do they come up with that rule? That's what we're looking at. Okay. So now the polynomial approximation is going to look like this. You already know how to find your point slope form. What's the point slope form going to look like? Yeah? This is your point slope form. Okay. We are going to use the point slope form to figure out how to expand the polynomial, because the function and the polynomial are going to be the same. So now we're going to expand the polynomial, p of x, or p of c in this case. Okay, so y here is going to be our general p of x. Okay, p of x minus y1 is our specific y coordinate, which would be p of 0, because that's our center, or f of c, sorry. f of c. Equals, slope would be f prime of c times x is our general x, which would be the polynomial x, minus x1, which is 0. In this case, c or 0. Okay, this is our general point slope form. This is what we are using to figure out what p of x is going to be. How do I rewrite p of x? Or isolate p of x?
Add f of c.
Add f of c. Okay, so our polynomial of a function or a series is going to be f of c plus f prime of c times x minus c. Now, this is true if it is a line, right? If I want to actually draw the shape as closer than if I draw a line, then yes. But that's actually not closer. I can still do better. What if I actually do a curve that is closer to that? Then I do the second derivative of it. What if I want to get even more closer? I do the third derivative, fourth derivative, and so on. So your expansion is going to look like this. If I actually want to do the specific expansion for e to the x, just with one derivative, it's going to look like this, okay? Because our f of x here is e to the x. And so will be our p of x. So the expansion for this is going to be, center is 0, f of 0 plus f prime of 0 times x minus 0. And so e to the x is actually, what is f of 0 in this case? 1 plus, what is f prime of 0? Also 1, because f derivative of e to the x is e to the x times x. So e to the x is actually 1 plus x. The expansion as a I know. But it's not exactly 1 plus x. This is just an approximation. But what if I had a second derivative? Then I can keep on going. The third derivative, the fourth. So this is going to be a bad approximation compared to when I do more derivatives. So if I do the second derivative, I will have a better approximation. So if I have to plug in, say e to the square. What is e squared on the calculator? Just put e squared on the calculator. 7 point what? 387? Now I can use this. What is 1 plus 2? 3. This is a bad approximation. As I keep going and going, if I add more derivatives, as I more derivatives, I'm going to get closer and closer to this approximation. Okay? So obviously one derivative is not enough. You have to do more to get there. Okay, so this one is called the first, you might want to write this down somewhere there. It's called the first order approximation. First order approximation, sometimes you will see the word first derivative or order, either way, or degree, either way, it's all the same. First degree, first order, all means you're gonna go up to the first derivative, okay? If it's a second degree approximation or second order approximation, then you have to go to the second derivative. Third degree, fourth degree, fifth degree, and so on. Okay. So that's what this whole thingamajiggy in the bottom is saying, that to improve the approximation, we have to make another second derivative at x equals c, and then we can keep on going. So in the last one, the second order approximation would look like this. This is first order, so second order will be P of x. In this case, our polynomial is e to the x. 1 plus x squared over 2 factorial, or just 2 in this case. Now, on the back, it wouldn't mean anything right now until we actually do some problems, then it will make sense. So this is second order. Let's say, how do I generalize this to any order? The nth order. That will be P sub n of x. Now this could be any function, it could be e to the x, it could be square root function, we will work with square root functions too, equals 1 plus first order approximation, second order, third order if you want, and so on up to the nth order. This is very specific to the function that you're working with. This is for e to the x. For cosine of x, it will be different because the derivatives are different for cosine. The derivatives are different for sine. The derivatives are different for square root function. Okay, this is only for e to the x. I'm just showing an example for e to the x. So now let's actually put all of these together and generalize this for any function that we want to approximate. Okay, we're going to treat that function as a polynomial and use a polynomial expansion for that. Are we good? Okay. Sometimes it might take more than fifth degree to approximate it as the calculator does. Obviously, that's what the calculator does it better because it's not doing it every single time. This code has been entered into the calculator in some way, so it's like a... Have you guys ever actually got curious about coding, not Ethan or Hillary, everybody else? You should probably go to Khan Academy just for fun and look at coding. It's like a flowchart. That's the word flowchart comes from. It is a flowchart. So if this is true, then this is what you're going to do. If this is not true, then this is not what you're going to do. That's all there is. And then it goes in a loop. And that's it. That's what goes in the calculator. So if f of x is a differentiable function, that means it has to be differentiable, obviously. If it's not differentiable, none of these is going to work. If f of x is a differentiable function, then an approximation, I'm reading it, but make sure you're writing this down. Oh, no, you're not writing this down here. This is just, don't write anything in the rectangle yet. So this one does not go in the rectangle box. Children, pay attention. Because that is very specific to e to the x. Are you listening to me? The one that is, I wrote in the previous, yeah, okay. This is in general, if I am asking you to write a Taylor polynomial series or Taylor polynomial approximation for any function, and obviously I will give you the center because without the center you can't do that. And this f of x is differentiable, it has to be true. F is centered around some number, x equals c. C is a number, okay? C is a number, not a variable here. Then this is how the approximation is going to be. It will be f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial.
Is there more?
Yes. No cheat sheet for these. Plus, Look at the pattern, children. Just look at the pattern.
Yeah, 3 factorial.
Yes. Triple prime x minus 3 cubed over 3 factorial.
Is there more?
We can keep on going, plus f to the 4. I like to use a Roman letter, but flipped math uses the normal number. I don't know. I just don't know. I guess it doesn't matter. This is the fourth derivative, by the way. That's what it is. Plus all the way to nth derivative of function times x minus e to the n over n factorial. Now, for you to remember, should you write over 1 factorial? Sure, but what is 1 factorial?
1.
1. But that's how it goes. I mean, you don't even have to write the 2 factorial because it's 2. But to memorize it, to see the pattern, it's actually easier to do the 2 factorial. Okay. This is called the nth order of approximation or nth degree of approximation. That's what it means. The more order you have, the better your approximation gets. Your calculator probably does it to the 10th or the 11th, I'm assuming, because that's how many decimal places it shows up. Okay. Maclaurin polynomial works. It's a special type of Taylor polynomial, except the center is 0. Okay, so the Maclaurin series or the polynomial is going to look like this. Pn of x, instead of c, we know it's going to be 0. So it's f of 0 plus f prime of 0 times x, because x minus 0 is x, plus f double prime of 0 times x squared over 2 factorial f triple prime of 0 x cubed over 3 factorial and so on to the nth derivative of 0 x to the n over n factorial. Now, do you have to memorize both the series? No, not really. You can memorize the Taylor series and then the Maclaurin series, you know it's going to be centered at 0. So you just have to not worry about the center. Okay? Okay, let's do some problems. When does this class end? 11 or 11:30? Oh, really? Huh. Okay.
Oh my goodness.
So we are going to find, it says the third degree. Can you see the problem? Okay, that means how many derivatives do we have to go? 3. So third degree or order, either way, it's the same thing, of Maclaurin polynomial. So which means, what's the center going to be? C is 0, 4, e to the 2x. You can put it on the calculator and it's going to approximate it for you. But we're going to do it by hand.
Amazing.
Okay, write it down. Every time you write down, your brain is actually thickening that synapses. We want third degree polynomial. F of what? X. X. We are not plugging in 3 yet. F prime of x times x. F double prime x squared over 2 factorial. F, we're going to stop at 3 because we only want third order. Triple prime of x, x cubed over 3 factorial. Okay. So now we need 3 derivatives of f of x. So I'm going to start with writing f of x is e to the 2x. F prime of x is what? 2e to the 2x. F double prime of x.
4e to the 2x.
And triple prime. Now you're gonna plug in, okay, here pay attention for a second. The x here is different from the x here. This is, we are approximating what would that f of x be, f of f prime of x be by plugging in, and then we're gonna put it in here and x will still stay. So f, what is the x? F of 0. This is the center. X equals c is the center, okay? Equals e to the 0, which is 1. And 8. This is a very specific point. The x here is a specific coordinate there, okay? Now we are going to write the general expansion, so make sure the x stays. I don't know how much room you have on that paper, but if you don't have enough room, just feel free to use a different. Okay, now the expansion for e to the x, for third order polynomial expansion, is going to be f of x, which would be what? E to the 2x. Plus, what is f prime of x?
2e to the 2x.
Oh, but we already have a 0 here. My bad, hold on. F of 0? Oh, did I mess up here? I did, huh? Okay. I messed up here, hold on. It has to be a 0. Okay, there we go. Now it's back. These are all just the coefficients that we are finding, okay? Here, let me clarify what we did. These are the coefficients of those terms. So that's why we are using all of these, okay? The first derivative, the second derivative, third derivative, those are all coefficients, like what is happening at that particular point. And then the equation is going to still have the x's. Just like when you write your point slope form, you find the coordinates, put it in, and then you'll still have your x and y. That's what this is. Okay, so f of 0 is 1 plus f prime of 0 is 2 times x. X is still there because this is the general equation format. Plus f double prime of 0 is 4 over 2 factorial times x squared. That's still there.
I got a 90 on my chem quiz.
Where did he go?
To the media center. I was waiting for my program manager, but she didn't even show up. But she told me to come there.
Plus f triple prime of 0, which is 8 x cubed over 3 factorial. Okay?
That's our equation.
Okay. Now we're going to simplify this. Four over 2 is 2 x squared plus 8 over 3 factorial. If you wanted, I would do it by hand. 4/3 x cubed. I just did the math on the side over there. But this is the third order approximation for e to the 2x. Are you guys with me? No, you're not. Stop nodding your head. Okay. Now, we are going to use our calculator to get the value for this, and then we're going to use a polynomial expansion to figure out how close we are to the approximation. Okay? So it says evaluate f of 0.2 and p sub 3 of 0.2. This is calculus way of approximating things. Are you with me? No.
Oh my God, I'm killing too. Are you okay?
Yeah. Oh, it's really bad.
Are you gonna have to calculate when they say
Oh,
She's gonna have to be remember what was it you
just have to do it, seniors. I'm relying on you. Frank Day, remember my one request. Senior Frank Day, what was the request that I had? Yes. Find a social studies teacher, because they don't ever use this. Or English teacher. Don't do Tanel or Tyson. Okay. Check them first, if they're good.
Just do that today. I go to the place.
Don't give me even worse marker than this.
Yeah, you see.
Okay. F of 0.2, what is f of 0.2? How do we find it?
We plug in point.
Okay, then plug it in. What are you waiting for? Well, hold on, where are you plugging in 0.2? E to the 2x, because f of x is e to the 2x. So then you're doing e to the 2 times 0.2. What is it? Give me 4 decimal places, actually.
1.4918.
Okay, so this is the better approximation. This is a calculated approximation. Obviously, calculator has a code or something that gives you better. But now we're using calculus to approximate that. When we use calculus to approximate it, this is what we wrote. This is a polynomial approximation method that we wrote. So now you're going to plug in 0.2 for x in the expansion and see if it is closer.
I'm doing all that.
What do you have?
I got 1.4906.
And 6 is repeating, I'm assuming?
Yeah.
Pretty close. Again, if we have 4th order, 5th order, 6th order, 7th order, 8th order, and so on, we get closer to that actual value. This is the actual value. Obviously, this keeps on going, but we can only approximate it.
Oh,
Cool? Okay. Let's do the second problem. I think I probably, hold on, did I not? What did I do? I thought there was another. Oh, I didn't do that. Okay, we'll do it tomorrow. It's fine. I didn't print that
I'm
part.
done. If
Okay.
it's one near the school.
Just like give up messages.
Stop distracting with Pokemon. Don't care about Pokemon.
How'd you know it was about that?
Oh no, it's super secretive. I have know nothing about you. It's so hard to figure it out.
I have other hobbies.
What, going to the gym and bulking up is not a hobby. Okay.
It is.
2. Find a 4th degree Taylor polynomial for f of x equals ln of x. Ah, the favorite word. I'm gonna find find a good portfolio problem for you all for this. Can't wait. This time we are centering it at x equals 1. It's not a Maclaurin series. It's a Taylor series. Okay, write it down. P sub 4 of x equals, how do we go? F of c. In this case, the c is 1. You can write 1 if you want. Plus f prime of 1, x minus 1 over 1 factorial. I mean, just f double prime of 1 times x minus 1 squared over 2 factorial plus f triple prime of 1 times x minus 1 cubed over 3 factorial plus f 4 of 1 over 4 factorial. Okay, let's test your derivative skills here.
I skipped number 3.
So starting with f of x is ln x. What is f prime?
1 over x.
What is f double prime? F double prime.
A negative 1 over x. Yeah, you see.
I can't be waiting for you all. We don't have time.
I was getting
F triple prime of x.
positive 1 over x. 2 over x cubed.
F fourth derivative.
6, negative 6.
Okay, now we're gonna plug in our center, which is 1. What is ln of 1? Okay, so now let's write the polynomial. F of 1, which is 0, so I'm not going to show that. 1 times x minus 1 over 1, it's just x minus 1. Are you guys okay with that? I'm just simplifying in my head as I'm doing it. F double prime, okay, I'll show that part, which would be negative 1 times x minus 1 squared over 2 factorial plus 2 times plus negative 6. Okay, now simplify all of those. Please don't put any decimals. Make sure it's in simplest fraction and not in decimals. Minus x minus 1 squared over 2 plus 2 and 2 cancels out. That will be 1/3 times that. 4 times 3 is 12.
Wouldn't it be
2 1/4. 1/4. Okay, if you wanna make it look nice here, you can do this if you want. I don't really care. But. Okay, so now we're gonna approximate the ln of 1.1. So f of 1.1, which is ln 1.1, which is
0.09.
give me, I don't know, I guess give me all the decimal places that you can see on the calculator.
0953 101.
Okay. Now we're gonna use our Taylor polynomial to approximate it. So b sub 4 of 1.1 would be, you're gonna plug in 1.1 in all of those. Do you guys know how to do everything in one step on the calculator? Okay, because these will, if you're doing it step by step, it's gonna take forever. We're gonna learn to put everything in one step. Make sure you put parentheses around the half, parentheses around the 1/3, parentheses around the 1/4 when you're putting those in. Do you understand what I'm saying? Like that. And when you do that, this is what you should get.
What missed you? He just answered me. You just woke up? I think he did. I think Anthony just woke up.
This is pretty close. Look, for the previous problem, we only got up to third derivative. This one is fourth derivative. 1, 2, 3, 4 decimal places. Even I would like, you know, the more we go, the better approximation is gonna get.
Ooh.
There is another problem that I'm pretty sure I forgot to print it out for myself, but I did it, but it's on my iPad. This one for question 3, it's asking for the coefficient of the third, what is it asking for? The third derivative, or the 4th degree, right? This is, pay attention for a second, everybody. When it's asking for the coefficient, we are only looking for these numbers in that term. So we don't have to do a whole lot of stuff. We don't have to expand it. We already know the third derivative. We do one more derivative, and then that will give us a coefficient, because these will give us a coefficients, right? But don't forget the factorial stuff. It's still part of the coefficient. You find this over 4 factorial, and that's it for that example. We can do it tomorrow if you want. I don't really, it doesn't matter. It's just a simple one. You have a question? Okay, there is a lot of